Hi everyone, my name is Chris. I will introduce to you oxide materials and TFTs. So I will first of all introduce what makes an oxide material by talking about amorphous state. Then I will talk about transport theory into the oxide semiconductors. Then explain what are the material trends, to see finally about thin film transistor, the different methods of deposition, which are basically vacuum and non-vacuum process. Then I will introduce some structures of this thin film transistor to show some performances and then talk about some issues. And also I will talk about especially solution process oxide TFTs and discuss what these issues are especially. Let me introduce to you the amorphous oxide materials. First of all, let's have a look on the different materials that we have. The different materials that can be used for oxide, such as the IGZO that I will introduce later, are referred as ionic amorphous oxide semiconductors, and their main characteristic is that they have a wide band gap, and also they don't have covalent bond, they have ionic bonds, contrary to, for example, amorphous silicon, which has been introduced to you by somebody else before. These oxide semiconductors can have very high mobility, and also they have some stability and very good performances. The amorphous silicon has been used, as you may know, for TFTs for the past years, and the oxide semiconductors have been introduced by the year 2003 with indium gallium zinc oxide that I will talk about a little bit just after. So the main difference with these two semiconductors is that there is the covalent bond, which is not present in the amorphous semiconductor, and also the band gap is wider in the case of oxide semiconductor. So how to make these oxide semiconductors? Well, there is a wide choice of atoms. These atoms are referred here from copper to bismuth, and the main choice is because of their electronic configuration, which is n-1 d10 ns0 with n more or equal to 4. And the thing is, why we use this one is because the overlap of these orbitals is superior or equal to 0.4. This probability gives a good transportation path for the electrons compared to others like the zirconium oxide or the oxide based on zirconium or hafnium, where the overlap probability is below 0.4. So in this case, when somebody uses zinc or indium or gallium or something made of these atoms, the probability to have a good conduction path is higher than others. Therefore, these materials can lead to semiconducting oxide semiconductors. But also, I'd like to mention to you that among all of these atoms, there are 15 of them. Some of them are basically a source of pollutions, such as maybe bismuth, or the other one like mercury, and therefore they wouldn't be used. And also, for example, gold is too expensive, so it cannot be used also. So this reduces the choice of the different atoms. And I have to say, to conclude for this this part, that the main choices are the zinc, the gallium, the indium, and the tin. And why? Why do these atoms are mostly used? So as I said before, they are not a source of pollution. They are not toxic as well. And but if we have a look at the different atoms' abundance on the Earth's crust and their cost and their worldwide production, we can see that actually the zinc is maybe the one which can be the most affordable, and also the tin can be the one which can be used easily. But if we have a look at indium, or for example even gallium, they are very expensive, and also their production is very low. So any material which involve indium or gallium would be somehow very expensive. So that's why some people, instead of trying to study indium, gallium, zinc oxide, they would study zinc tin oxide. Also, the main issue is for the high volume manufacturing. The the people have been studying IGZO because it's very easy to produce metal targets, and it's also very easy to etch. So in a process involving this material, is very easy and convenient to use, whereas the zinc tin oxide is very difficult to etch. So the process making of any thin film polyester using zinc tin oxide by sputtering especially is quite difficult for zinc tin oxide. But for IGZO or related materials such as IGO or indium zinc oxide, this is very easy. So we've seen how to select the different atoms. We've seen also how and why these atoms are used together, and why this product development is very easy for indium, gallium, zinc oxide, why it is studied. Now let's have a look at the different oxide materials. There have been many oxide semiconductors. As I mentioned before, there are like 15 atoms that can be used, except the one which are toxic or can be a source of pollution. And the other one would be to make PN junction. So the material which I introduced, the indium gallium zinc oxide or the zinc tin oxide or their family, which means gallium oxide, gallium indium oxide, or zinc indium tin oxide, they are n-type semiconductors. So the other semiconductors would be p-type, and the idea would be, of course, to make whether PN heterojunction or PN homojunction. So this would mean using two different kind of semiconductor, maybe indium gallium zinc oxide for the n-type, and maybe another p-type material which could be from this family, copper family, copper indium or lanthanum copper oxide something. And this material would be used for diodes or for LEDs, or the main idea would be to reach stable electronics, stable amorphous oxide devices which are transparent, and also that can be used for flexible electronics. So we want to do amorphous oxide semiconductors, but also oxide conductors with a high conductivity. The one which is used mostly is ITO, and the main idea also, if we want to do very high transparent material, we need them to be over 80% transparent in the visible region. And this is the case for most semiconductors, oxide semiconductors, because their band gap is very high, very big. So now let's have a look at the different covalent and amorphous states of the different amorphous semiconductors. What is the difference of ionic and covalent semiconductors? The main idea for the covalent semiconductors, for example, this silicon. Silicon, in the case of a crystal, we can have very high periodicity in the crystal, and the orbitals overlap easily. Therefore, the conduction path is very good. But in the case of amorphous, there is sometimes no link. There is some voids, and also there could be some dangling bounds, which means that the atom is actually connected to nothing. So to get an electron to go somewhere, it's very difficult, because there are traps, the dangling bounds, and also the different angles and the bonding lengths are quite different from the crystal case. But in the case of ionic oxide semiconductors, well, the main electron path goes through the ns orbitals, and these ns orbitals are well connected, whether in the in the crystal case or in the amorphous case. Therefore, the mobility is slightly different, but not so much. For example, in the case of the crystal, for the oxide semiconductors, the mobility can be as high as 100, but in the case of amorphous, it can be 10 to 60. In the case of crystal covalent semiconductors, for silicon, we can reach easily very high mobilities, more than 100 centimeters square per volt second. But in the case of amorphous silicon, this mobility fall down to 1 centimeter square per volt second. The case of IG0, indium gallium zinc oxide. So if we want to have a look about this material, we should have a look at the different material properties depending on the ratio of the different materials. So we have gallium, we have zinc, and indium. And here are different examples of mixtures. So here is, for example, a mixture around 111, and this gives, for example, the mobility, and we can have very good mobility, and around 9 centimeters square per volt second, with a carrier electron concentration up to 5 times 10 power 18 per centimeter cube. And if we have just, for example, gallium indium oxide with a ratio of 1:1, then we can have mobility which is around 0.9 centimeters square per volt second, even though the carrier concentration is the same. And if we have indium zinc oxide, we can have a very nice mobility, around 39 centimeters square per volt second, and a very high carrier concentration, around 10 to the power 20 centimeters per cube. Also, if we have a look at the structure of the materials, the materials are, when the mixture of the different materials, the indium gallium zinc oxide is amorphous. And when we just have indium oxide or zinc oxide, these materials are crystalline, and this impacts, of course, the mobility. As we can see, the mobility was higher when we had only the indium oxide or the zinc oxide, but in the case of the amorphous state, the mobility was a little bit lower. Also, the thing is, because of the different process condition and the use of suitable gate insulator or contacts, so in this example they use ITO, indium tin oxide, which is very nice conducting oxide material. They use it for the source, the drain, and also the gate, and they use yttrium oxide for the gate insulator, and they can obtain very transparent TFTs and also very good performance TFTs. The other characteristics, so as I introduced before, the oxide semiconductor should be very transparent if you want to make flexible or flexible transparent TFTs. And the thing is that in the case of transmission over a wide range of low wavelengths, the transparency is somehow not dependent in the visible region from the 400 to around 800 nanometer. This is basically the same, but for different carrier concentration at higher wavelengths, the transmission is highly dependent. And concerning the material, as I mentioned before, the indium gallium zinc oxide, it depends on the proportion of the different atoms, the indium, the gallium, and the zinc. But most of the time, this material is amorphous. Here, this XRD pattern shows that there is actually no peak. So no peak means that there is no crystal phase. This small shoulder is just maybe related to the glass, so it's not depending on the IG0. Also, to finish with some electrical properties of the material, the mobility is depending on the carrier concentration, and it is highly dependent on the temperature. But the carrier concentration is not dependent mostly on the temperature. Also, the different trends of the oxide semiconductors. So there were zinc oxide. There has been IG0 for the past almost 10 years, which was introduced by Hosono Group in Japan. And then zinc tin oxide has been introduced. IG0 has been, as I mentioned, widely studied, and also IZO and other related compounds such as indium zinc tin oxide, for example. Let's have a look at thin film transistor based on oxide semiconductors. How to deposit them? There are different techniques. One of them is the vacuum deposition, sputtering, and PECVD, which stands for plasma enhanced chemical vapor deposition. So these are widely used techniques in the TFT industry, in the display industry, and the main issues of this vacuum deposition is the efficiency. It is very expensive. This deposition machines are very expensive, and also the size is huge. Here you can see depiction of a man compared to the wide of one PCVT machine, and you can see that it takes a lot of place. But there are other solutions, such as solution process, such as solution coating, spin coating, or printing. The main idea, the main focusing for this process is because it's very simple to make anything. The maintenance is very easy, and it costs almost nothing. The spin coater also is not on size at the same size as this image here. It's actually very small. But if you want to do inkjet process, you need an inkjet printer, and this inkjet printer, even though it takes small space, it doesn't take as much space as a PECVD machine, and also the maintenance is quite simple, and it's easy to do processing. The only issues are related to the process reproduction. It's maybe difficult to have always the same TFTs over the different processes. Yet in these processes you can do many TFT structures. So it has been introduced examples of structures such as back channel edge, bottom gate structure. So the gate is deposited, and then the gate insulator, and then the IGZO, then the source and drain, and finally the passivation layer. The edge topper type, which is the mainly used in the oxide TFTs. The main reason is that the IGZO back channel is very sensitive. Actually, any oxide semiconductor is sensitive to environment. So when we do the process in the vacuum chamber, we need to deposit IGZO or the oxide semiconductor, and then without breaking the vacuum, we need to protect this oxide semiconductor by depositing some SiO2 or some other material to protect this semiconductor. Other structures which are more conventional, such as the coplanar structure and also drain offset, have been also introduced and studied. And in the case of non-vacuum process, so it means solution process, spin coating, or inkjet printing, the main TFT structure is the bottom gate bottom contact. A bottom gate top contact also is used. Why? Because the zinc tin oxide, for example, the oxide material, which is deposited by inkjet printing, is the final step. So as a channel region is the final step to be processed, then the other material should be deposited before. That's why this TFT structure is used. Finally, I would like to introduce about the printing advantages and printing overview of the different materials, oxide semiconductors. So, as I mentioned before, it's low cost, it's very simple to process anything, and also it requires fewer process mass compared to other material. Also, it has a high efficiency, and the only issues would be to reproduce the characteristics. Compared to other oxide semiconductors such as IGZO, zinc tin oxide has been widely introduced and studied in the case of printing and solution process. Why? Because, well, compared to IGZO, you need only 2 atoms, so the ink formulation is more simple. Also, the stability of the ink, which is necessary to print and to form a good channel, is necessary to have. So ink stability may be one option which has to be regarded as important. Also, it gives high quality thin films, and the TFT characteristics are very good. If we have a look at the different materials which can be introduced, which can be printed, we have the oxide and we have the organic. In the organic case, we have small molecules and we have polymers. The maximum temperature is below 200 degrees, but the mobility is around 1 to 7 usually. And the issues related to the organic are stability and the mobility. But in the case of oxides, it's very easy to get mobilities higher. It can be over 40 centimeters square per volt second, even higher have been reported. But the main difference is in the case of what is called Solgel process. The Solgel process means that you are using precursors which will interact in the solution, and then you will print the solution and another material will be formed. So you use zinc precursor with a tin precursor, for example, and you mix them in a solvent. This zinc and tin will form whether some complexes or something else. Then you will deposit this solution of zinc and tin, and by annealing they will form oxide semiconductors. So there have been two families of precursors, chloride and nitrate basically. This has been the two main options. There have been new introduced precursors, but I will just introduce these two families which have been widely studied. The main issue is the temperature, annealing temperature. It has been shown that temperature over 300 degrees is needed, so you cannot make, or it is hard to make, very nice performance TFTs or devices on flexible substrate. This flexible substrate, they need very low temperature, lower than 200 or around 200, so it's difficult to use these materials for flexible devices. Also, the main difference between these two families is the resulting material and mobility. Mobility for nitrate precursor gives rise to mobility around 1 and with a high temperature, but the chloride is possible to have higher mobility with a somehow smaller temperature. But the main issues is that there have been very few reports on transparent TFTs and also on flexible substrate. And the case of nanoparticles so far has been not so much introduced because the mobility is very low and the reproducibility is very poor. So finally, to talk about the different TFTs, the vacuum one. In the case of the vacuum one, the TFT is the first one which has been reported. This one is not amorphous but single crystalline, but still the mobility was very high, and it was depending on the gate insulator which was used. In the case of hafnium oxide, the mobility was around 80 centimeters square per volt second, while in the case of aluminium, only 2 centimeters square per volt second. And as I said before, transparency is very high, over 70%, and the performance of this first IGZO TFT shows a nice on-off ratio. It's around 10 to the power 6. And so the conclusion, one of the first conclusion, is that there is a high dependence on the gate insulator. There is it's a very possible to get very nice TFT characteristics, and the introduction or the making of transparent, flexible oxide TFTs is possible. Today's main challenges for oxide TFTs are the following: P-type materials and light impact. P-type materials, why? Because the the valence band is a form of localized states, so it's very difficult to make very valuable P-type materials. Therefore, people have been trying to make very nice TFTs, but the mobilities are very poor, usually less than 1 centimeter square per volt second. Also, in the case of this P-type, so here is tin oxide. Tin oxide usually is N-type, but by certain process condition it's possible to make it P-type. And so, depending on the channel thickness, the smaller the better the TFT characteristics. But as I mentioned before, the mobility is very poor. So there have been other oxide, P-type oxide semiconductors which have been tried, such as the copper oxides family and other materials. And also one of the main issues is the light effect. Why? Well, the why is actually not very well understood, even though it's a question of diffusion of the different electrons and holes which are generated from the light. But as we can see from this figure, for example, when you have a certain wavelength, and depending on the wavelengths, the shift of the TFT characteristics is less, bigger or less. So for very small wavelengths, the shift is high, but for higher wavelengths, the shift is lower. And also, the main issues that I will talk is for the non-vacuum process, the solution process. The first one which was reported for IGZO was in SID conference, where they had a mobility of around 1 centimeter square per volt second, and they could have nice properties, but the annealing temperature was quite high, around 450 degrees. So the main issue for the solution process has been to reduce this annealing temperature. So people have been using different annealing temperatures. 600 degrees showed a very nice saturation mobility of around 10 centimeters square per volt second, and others have used different techniques such as pyrolysis to reduce the temperature. And we have introduced another way to think about this reduction of temperature in order to get high mobilities. And the main options these days, the new options that have been introduced to get very low annealing temperature, is by using different precursor or different annealing techniques. And this can lead to very low annealing temperature, as low as 230 degrees, and they can have mobilities of around 8 or 10. So the main issue is the temperature. And finally, I will introduce, but it has been introduced by others, some characterization techniques. So to get the saturation, the mobility from the saturation region, you need this equation, which is widely known, and the mobility is taken from the square root of ID versus VG, and the VTH is taken from the intercept of the slope of this curve. And also it's possible to calculate the mobility from the linear region using the transconductance. And here you have the different characteristics. L is the channel length, width for the W, and Cox is the oxide capacitance per oxide per unit area. And here are some examples that we have. So for very low VDS with a VGS ranging from -5 to 5, and we have very nice transfer characteristics using zinc tin oxide and aluminum oxide as a gate insulator. The mobility is around 30. And here is an example of TFTs that we have made, and they are transparent, and they are based also on zinc tin oxide, but here the gate insulator is SiO2. Thank you very much for your attention. Have a good day. Thank you. Goodbye.